So today we're going to start another chapter, a new chapter, chapter 13, physical properties of solutions. So this is, first of all, a solution. We'll get to the definition of that. This chapter does have a little bit of math in it. So it also involves stuff with moles. We did one unit of concentration before in a previous chapter, and we measured concentration and molarity, concentration of a solution, and that's going to be in this chapter as well. And we'll also talk about different measures of concentration and not just molarity in this chapter. Okay, so let's just get started this chapter. So properties of solutions. Actually, before I go on, this picture here is a plane, obviously, being sprayed down with a solution, and a solution that lowers the freezing temperature. We'll get to one of the properties of solutions, that is when you dissolve something in, say, water. Let's just assume what we're talking about, the substance is just water right now. When you dissolve stuff in water, you lower the freezing point. We'll get to why later on in the chapter. And so they spray down airplanes with a solution that lowers the freezing point. And they do that on purpose because it keeps ice from developing or building on an airplane, which could affect the aerodynamics and the safety of the airplane. So to make sure that any ice is just washed off and no ice can form in places where it snows and freezes, obviously not here in LA, they spray down airplanes with a specific type of solution. What is the specific solution? I don't know. I don't know what the specific solution is that they use on airplanes, but it could be almost anything. Okay, but obviously you wouldn't want to use something like salt water, because that will just probably make it rust or corrode faster. Another property of solutions is something called the Tyndall effect, which is what this thing demonstrates. That is, it reflects light. When you have a beam of light going through a solution, it may reflect back or scatter some of that light back at you. If this is completely clear, like just pure water in it, nothing in it besides pure water, you should not see, at least not much, light being scattered back. But as you probably would guess, if you put stuff in it, you can start seeing light being reflected back or scattered back. And that's something called the Tyndall effect, which is later on in the notes as well. Anyway, so those are just some properties of solutions. Let's start with the definition of solution as well as parts of a solution. A solution is a homogeneous mixture of two or more different substances. So you have two things in it, at least. Okay? Solution is a homogeneous mixture, meaning that it's equally spread out throughout. So it's equally spread out throughout. There is a homogeneous mixture. We talked before in a previous chapter about heterogeneous mixtures like salad or sand. It's a mixture where you can actually see the different parts. A solution is a homogeneous mixture that it's mixed up equally throughout. There are two main parts to a solution. They're the solute and the solvent. This is our textbook's definition. It says a solute is a substance present in smaller amount, and a solvent is a substance present in larger amount. And that'll work fine for something like a gas and a gas mixture like the air. The air is roughly about 80% nitrogen, 20% oxygen. I know there's other things in it, but I'm just talking roughly. So your solvent, therefore, the larger amount would be the 80% nitrogen. And a solute, you can say, is the 20% oxygen. Yes, there's also carbon dioxide, all those other gases in it, but I'm just talking about the main stuff right now. So that would work fine in that definition. This is not necessarily the best definition. That just comes from a book. In other books, they define a solute as a substance being dissolved and a solvent as the medium in which it's being dissolved. So if you say you dissolve some sugar in water, let's not even care about how much, or let's say they're equal. I have equal amounts of, whether it's by mass or by volume, I have equal amounts of sugar dissolved in equal amounts of water. First of all, you're like, well, based on that definition, neither of them's a solute or solvent, or maybe they're both a solute and solvent because they're equal amounts, not smaller nor larger. So that's why I like some other books' definition that say a solute is a substance being dissolved, and a solvent is what is it being dissolved in. So sugar dissolved in water. Sugar is your solute. Water is your solvent, regardless of the quantity. So if I say X dissolves in Y, doesn't matter what X is or what Y is, or even how much X or Y you have. X is your solute, Y is your solvent. And there's many different types of solutions. You have liquids and liquids, like soda, soda water, like, well, obviously soda. Sorry, this is a gas in a liquid. I'm looking at the wrong thing. Gas in a liquid, like soda water, which is a gas in liquid. You have liquid and liquids, like alcohol in water. You have solids and liquids, like salt. I said sugar in water, but it doesn't matter. You also have solids and solids, so like brass or solder. They are a mixture of different types of metals. Um, and yes, gas and solids are not so common, but like hydrogen and palladium. Some gases dissolved in a solid. Okay, so there's different types of solutions. In this chapter, I believe we're primarily going to be doing stuff dissolved in liquid. And, like in chapter about aqueous solutions, our most common solvent, also known as our universal solvent, is water. So if it doesn't say specify otherwise, and you just say, oh, it's it's a solution, first thing you probably think is going to be mixed in water, unless otherwise stated. So that's one common thing. Usually we're talking about dissolved in water. Okay, going on. Now, when we get solutions, they come in three main types: saturated, unsaturated, and supersaturated. Maybe I'll start with, well, the first one, saturated. Contains a maximum amount of solute that will dissolve in a given solvent at a specific temperature. Let's say I add a cup of water, and of course, you can put some salt in it. Let's just say I'm dissolving salt. I have a cup of water, I put a teaspoon of salt in it. I stir, of course, it'll dissolve. I put another teaspoon of salt, stir, it'll probably dissolve. Well, eventually I'm gonna get to a point where I can add salt, but I stir, it will not dissolve anymore. Whatever that point is for that given quantity of solvent at, or assuming room temperature right now, once you get to the point where it will not dissolve anymore, the maximum amount, you have what's called a saturated solution. So it contains a maximum amount. If you have less than the maximum, then you have what's called an unsaturated solution. Contains less solute than the solvent has the capacity to dissolve at a specific temperature. So again, let's say my cup of water at room temperature can dissolve, I'm making this up, let's say it can dissolve 5 teaspoons of salt. If I dissolve 2 teaspoons of salt, well, it can dissolve more. It's considered unsaturated. So some terms, some places where you might have heard saturated and unsaturated are like saturated fats and unsaturated fats. And what is it saturated with? It's hydrogen. Okay, so fat molecules that have maximum number of hydrogen atoms attached to it's called a saturated fat. And usually these saturated fats form long, rigid chains. And because of that, they're usually solids at room temperature. Unsaturated fats, which do not contain the maximum amount of hydrogen on those fat molecules, they are usually liquids at room temperature. So in case you ever heard like saturated fats, unsaturated fats, that's the molecule, the fat molecule, if it contains a maximum amount of hydrogen, is called a saturated fat. Okay, then there's another one, right? Supersaturated. Supersaturated solution contains more solute than is present in a saturated solution at a specific temperature. You're like, wait, how can I have more than maximum? Then what's the point of the term maximum if you can have more? Well, remember, they all say at a specific temperature. So let's get to my cup of water at room temperature. Let's say at room temperature, I can put in 5 teaspoons of salt in it, NaCl, sodium chloride, stir, it dissolves, and any more, it won't dissolve at room temperature. Well, this is at a specific temperature. What if it was higher than room temperature? It was not room temperature water, but you had boiling water. As you probably knew or kind of guessed, you can dissolve a little bit more. So let's just say at boiling water, you can dissolve 6 teaspoons of salt. But at room temperature water, you can only dissolve 5 teaspoons of salt in it. Well, if you dissolve 6 teaspoons of salt in boiling water, but you let it cool back down to room temperature, then it would contain more salt or your solute than you should for a saturated solution at room temperature. Well, when that does happen, okay, they will probably crystallize out. I didn't say quickly. Here are pictures of sodium acetate crystals rapidly form when a seed crystal is added to a supersaturated solution of sodium acetate. So if I had a supersaturated solution of salt water, and I put a tiny grain of salt, so where the salt crystals can start growing, then I'm not going to say it's going to be rapid with salt itself, but within time, it will grow the extra salt crystals in it. The supersaturated solution will crystallize out until you just have a saturated solution. So that is so that's a definition of supersaturated solution. Okay, or skip the slide for right now. Come back later. Okay, so we're also going to get to something about, there's a term that's called like dissolves like. What that means are molecules of similar properties will dissolve other molecules of similar properties. Well, it's written there. Two substances with similar intermolecular forces. When I meant properties, intermolecular forces. With similar intermolecular forces are more likely to dissolve in one another. And for instance, a nonpolar molecule dissolves other nonpolar molecule. So remember in our last chapter, we talked about whether a molecule is polar or not. So these two molecules are nonpolar. They will more likely dissolve in each other. Polar molecules dissolve in other polar molecules. So ethanol, alcohol, will dissolve, which is polar, will dissolve in water, which is polar. So nonpolar dissolves nonpolar, polar molecules dissolves nonpolar. Ionic compounds also dissolve in polar because ionic is something positive, negative, and polar means that it's, remember, partially positive, partially negative. So polar dissolves in polar, nonpolar dissolves in nonpolar. Ionic, which is kind of like polar, it's positive, negative. Ionic things will dissolve in nonpolar stuff. I'll pause for a second. Okay, I wanted to show you this. This is actually later on in notes, but I want to show you this now of how kind of soap works. Soap molecule. Okay, so this is a large picture of Lewis structure of soap, where if you just cut off this end, the right side, the long chain part of the molecule is nonpolar. Now, this side of the molecule, the far right side of this molecule, or the Lewis structure, is polar. You have some positive side and oxygen, which is pretty electronegative, a negative side. And so you have a polar part of the molecule, you have a nonpolar part. Polar things like to dissolve in other polar things. Non-polar things like to dissolve in other non-polar things. Polar things, this is a diagram of, this is supposed to represent this soap molecule, where you have non-polar part and a polar part. It says hydrophobic and hydrophilic. Hydrophobic means that, like phobia, is afraid, does not like to be dissolved in water. Hydrophilic means that it likes or will dissolve in water. Why? Because water is a polar molecule. This part of the molecule is polar. The other side of the molecule is nonpolar. This part of the molecule is nonpolar. Well, when you have grease, oils in general are nonpolar. Just telling you that right now. Most greases are nonpolar, which is why when you have grease and you put it in water, they don't really mix. Oil and water in general don't mix because polar molecules prefer to attract to other polar things. Nonpolar attracts to other nonpolar things. Well, soap molecule is partially nonpolar, partially polar. The nonpolar part of the grease molecule is attracted to the nonpolar part of the soap molecules. So the soap will dissolve grease. Well, that's great. But how does that help us clean, like say clean our hands or laundry? Well, the polar part of the grease molecule, this right side or the circle side here, the polar part of the soap molecule is attracted to polar things like water. And so this polar part is attracted to water and it lifts this grease off of, say, my hands or your clothes if you're doing laundry, and will dissolve with the water. So although grease, oil does not really mix with water, when you add soap to it, where it is nonpolar, the nonpolar part of soap attracts to the nonpolar part of grease, and the polar part of soap attracts to the polar part of water. That's how soaps in general work. Okay, so that's what we're going to just have for today.